Okay, so this lecture immediately follows the lecture talking about estimating water demands for municipal systems, and in that lecture also included estimating fire demands. Now we want to talk about demand variability, specifically with regards to how does demand vary within the course of a single day, and also how does demand vary at different parts of the year. In the previous lecture, we talked mostly about average demands, estimating average demands, and today we're going to be talking about how does the actual demand vary. So first, we're going to look at the daily variations in water use. And you can look at these graphs here, and what these are called, you can see that in the title of one, is called a diurnal curve. And diurnal curve just means daily curve or daily pattern of use. The one on the right that says typical diurnal curve, this is actually from the American Water Works Association, AWWA. And the AWWA diurnal curve is sort of the generic industry standard for what the pattern of water use during the day looks like in a typical modern developed world system. And often we don't have a good diurnal curve for our cities or areas that we're planning for, and so we might use something like this as just kind of a default if we don't have anything else. You can see one on the left as well that is from the book, and it looks pretty similar. So below that, you can see peaking factor, the ratio of the hourly demand to the average daily demand. So the peaking factor on the graph on the right is on the y-axis. One is says, hey, the demand is equal to the average daily demand. But you can see at its peak up here at the top, we have a peaking factor of 1.8. And what that means is that at that point on the curve, the actual demand is 1.8 times the average daily demand. So if I took each hourly demand factor, peaking factor off of this graph, they should all average out to 1, which would be equal to the average day demand. So knowing now what a peaking factor is, we can say what is the peak hourly demand factor, the highest peaking factor for any hour of the day. Well, if we're using the AWWA curve, then our peaking factor is going to be 1.8. But if we are not, if it's unknown and we're not using AWWA, sometimes we use 1.8. Also 2.0 is a typical generic demand factor to use as well, peak demand factor. So whatever we come about for our average day demand, if we want to know what is the peak hourly demand, we're going to multiply that by either 1.8 or 2 to get that hourly demand. Okay, what about variations over the course of a year? So seasonal variations in water use. Outdoor water use makes up a really large percentage of total domestic use. But outdoor water use is highly seasonal, whereas indoor water use is pretty much constant through the course of the year. So if I look at these graphs down here, or this graph, it's comparing water use consumption in Phoenix versus Portland over the course of the year. And you can see that in Portland, we could kind of draw a line here that says, look, in the winter, our water use is all indoor, and that black line I just drew is going to indicate sort of our indoor water use over the course of the entire year, whereas then this area would be pretty much an estimate of the outdoor water use that's occurring mostly during the summer. Same thing for Phoenix, but Phoenix obviously is going to be higher amounts because they're going to use more water outdoors. So we have this other thing called the peak day demand factor, which is going to be the ratio of the daily demand during the maximum demand month to the average daily demand. So let's think about it here. So Portland here, we're looking at, if we looked at all of these monthly demands throughout the year, let's say they vary from 10 to 23 or something like that. If we said, let's say the average was 15. I'm just making this up. Now we say our peak month here is July, and let's say July is 22. Well, in that case, our peak day demand factor is going to be equal to 22 over 15, which is a little less than 1.5. Let's see. That's 22 divided by 15, 1.47. And if we don't know what this is, here we have some actual data to derive this from. But again, if we don't know what that is, a general generic number might be 1.5. And that's kind of the default to use if we don't have any other good data. So that's going to be the peak day demand factor. And obviously now I have I have an average demand, a peak day demand factor, a peak hourly demand factor. And in a second, I'll kind of put all those together. But depending on what element of the water supply system you're designing, different capacities or demand criteria are required. So as an example, you could have pipes, right? I've talked about this a little bit. The pipes have to be able to transmit the peak flow ever experienced within the pressure requirements. So we're going to have to look at the peak hourly flow for that. Whereas pumps, as we indicated, if we have storage included downstream, the pump only has to pump sort of at the average daily demand. All of the peaking within the day is going to be covered by the fact that the tank level is going to fluctuate and we have some water in storage. Similarly, the tank itself is going to be sized for, storage for the course of an entire day, not for like the peak hour, for example. So we need to understand all these different demands and these demand factors if we're going to fully design a water system. Okay, so what are our final outcomes for design? Let's put this all together. We've got our average daily demand. This is the total water demand volume over the course of a year divided by 365, or the average of each daily demand value for all 365 days. This is similar to what we were doing in the previous lecture. We're going to just start on average in a day, what's the average daily demand? But then we say, look, it varies throughout the course of the year. So this peak day demand is the total water demand on the highest water use day of the year, which is often derived from ratios of monthly demands. So let's write out this equation. Our peak day demand is going to be our peak day demand factor times our average daily demand. Average day demand, of course, for over the course of the whole year, we multiply that by the peak day demand factor, which might be something like 1.5, to get to what would be the peak day in July or August. Reminder, we often use a whole month as a surrogate for this. So in other words, we kind of would assume all of the days in August are the same flow. They all are the peak day demand factor or the August demand factor times the average day demand. The peak hour demand then is the total water demand for the highest 1 hour period on the highest water use day of the year. So our peak hour demand is going to be our peak hour demand factor times our peak day demand. So once we figure out what is our highest water use day of the year, whether it's July or August, usually, then we're going to multiply that by the peak hour demand to get what is the peak demand during the highest hour of that day. Okay? So let's do an example problem here. Pretty straightforward. We got Newtown, the community from the last set of notes that we did the example problem in the previous lecture, had the following monthly water usages last year. Part A, what is the average daily demand? Okay, so let's look at this table. We've got the months January through December, the demand for that month in million gallons per day. So million gallons per day is a flow rate, right? It's a volume per time. And that is going to be the average flow rate for that entire month. And then at the bottom, we're averaging all of those months together. So what is the average daily demand? The average daily demand is just the average of the entire year. And it's already stated there as the average of all of these months, which the months, again, are the average of all of the days. So we can say, well, this is just 0.573 MGD. That's the average daily demand over this whole period. Okay, so then what is the peak daily demand and what is the peak day demand factor? Well, we can look through and just see the highest value in here is August, and its value is 0.773 MGD, million gallons per day. And again, we're assuming all the days in that month have 0.773 MGD demand, so that there is our peak daily demand. What about the peak day demand factor? Well, the peak day demand factor is going to be equal to the 0.773 divided by the average daily demand, 0.573, and we get 1.35. All right. Part C, what is the peak hourly demand using the AWWA diurnal curve peak hour demand factor? So again, I don't have data here about what the diurnal curve looks like, so I'm just going to use a generic value, and I'm going to say I'm going to use 1.8, which is my AWWA peak, times, and now it's important that I use the peak day demand, which is from part B, not the average day demand, to get this peak hour demand. So 1.8 times 0.773 MGD, and I get 1.39 MGD. And part D, a single pipe leads from the main part of town to the shopping center located right off the interstate. What is the maximum flow that this pipe should be sized for? So back in the water distribution system set of notes, I noted that pipes should be sized for, generally speaking, peak hour demand plus fire flow. In part C here, we've just established what is the peak hour demand. It's 1.39 MGD, but we need to account for fire flow. So it's going to be 1.39 MGD plus fire flow. Well, in the previous set of notes, we looked at what the fire flow for the shopping center was, and it was 5,500 gallons per minute. I need to convert this to million gallons per day. So multiply by 60 minutes per hour, multiply by 24 hours per day. So my hours cancel, minutes cancel. I'm at gallons per day. I need to get to million gallons per day. So I multiply by 1 MGD per million gallons. And now, if I cancel the 2 million gallons, this million gallon and this million gallon, I'm going to have days. So I get 1.39 MGD. This whole thing above comes out to 11.52 MGD. Together, those are 12.91 MGD. So most of the flow that I have to size this pipe for is coming from the fire flow and not the peak hour demand, because again, I'm fighting a fire here. I need a lot of flow all at once, and the pipe has to be sized for that. Okay? So that concludes our little mini lecture on variability in demand throughout the course of the year and hourly as well.